Hello everyone, my name is Weijie Wang. I'm a PhD student from Yale University. And today I'm going to present BalanceProofs, maintainable vector commitments with fast aggregation, which is a joint work with Ulichney, who was an undergraduate at Yale, and my advisor, Charalampos Papamanthou. So to begin with, I'm going to introduce what are vector commitments. So vector commitment is a short commitment to an ordered sequence of values. So with that value, the prover can compute the individual proofs for each location to prove that in each location, the value is indeed something. So vector commitment has algorithm like commit, which computes the digest, open all, which compute all the individual proofs, update all, which update all the individual proofs in one algorithm, and aggregate, which just takes some individual proofs as input and output the aggregated proof and verify. So vector commitment has correctness and soundness property, while the soundness property is actually position binding, which means the adversary cannot forge proofs for different values of the same location. We also introduced two other properties. The first one is maintainability, which means the update all algorithm is sublinear to the size of the vector, and aggregatability, which means the size of the aggregated proof is sublinear to the size of the index set we do in aggregation. So let's see an example, Merkle trees. Merkle tree is actually one kind of vector commitments. So here the digest is a Merkle root. And the open all algorithm is just to compute all the hashes in the Merkle tree. And considering update all is just to recompute the hashes in the path from the root to the leaf. So of course, Merkle trees is maintainable since the update all algorithm is just O log n time. And I'm not saying that Merkle trees is not aggregatable, but it seems that without snark or similar arguments, we cannot do aggregation efficiently. Also, vector commitment has application in verifiable storage, stateless blockchain, and more. So there are two types of vector commitments. The first type is not maintainable, but with fast aggregation. So in this type, we have ASVC and point proofs. So for example, ASVC, so given a vector, they compute the Lagrange interpolation over the vector to get a polynomial. And they compute the KZG commitment of that polynomial to get the digest. So it's a vector commitment with linear time aggregation and constant size aggregated proof. But when it comes to update all, it seems they have to use linear time to update all the individual proofs. So it's not maintainable. Type 2 is maintainable, but with slow aggregation. In this type, we have Merkle trees, as I said before, and Hyperproofs, which is also a tree structure commitment, but they use inner product arguments to do the aggregation, which is not very practical. So now we introduce BalanceProofs, which is the first vector commitment that is maintainable with fast aggregation. So here I show a small table. We can see that although our update all time is like 3 times slower than Hyperproofs, but our aggregation time is much more efficient and practical. So let's see the details of BalanceProofs. So BalanceProofs is essentially a compiler which takes a vector commitment scheme as input and output another vector commitment scheme. So here we pick ASVC as the input scheme. ASVC has nlogn time to open all m proofs and constant time to update each individual proof after receiving an update request. And then we have the output scheme, which has square root of nlogn time to update all proofs and the square root of n time to query any individual proofs. So let's see how it works. So at the beginning, we have a vector, and we compute the digest and compute all the individual proofs, and we have everything locally. When we receive an update request, we just put the update request into a record list. and update the vector we have locally, and update the digest if necessary. When we keep receiving update requests, we put those into the update record list and update the vector we have locally. When the number of records reaches square root of n, we use nlogn time to open all proofs from scratch. So right now, the individual proofs we have locally is all the latest one. And now we can clear the record list. Anytime if we need to get the proof for some position j, we apply each update in the record list to pi j. That's the individual proof we have locally, and get the new proof pi j prime. That is, this works because ASVC has constant time to update each individual proof per update request. So above all, we have amortized nlogn over square root of n, which is square root of n log n time to do the update part, and we need at most square root of n time to get any individual proofs, since the size of the list is at most square root of n. After we get every individual proof, then we can do the aggregation. So the main problem here is that we need one update that requires nlogn time to open all the proofs. That is, we want to avoid. So we can use amortization technique to improve this worst case. The basic idea is that we can separate the algorithm to open all proofs into square root of n steps. And then we extend the maximum size of the update list to 2 square root of n. So when the size of the list reaches square root of n, we start the first step of the open all algorithm and finish the open all algorithm in the next square root of n steps. So that when the size of the list reaches 2 square root of n, we have already finished the algorithm for the first square root of n updates. And now we can remove those square root of n updates in the list and start the open all algorithm from, for the updates from square root of n plus 1 to 2 square root of n. So repeat this over and over again. We will have an algorithm which has the square root of n log n time to update, and that is the worst case. Furthermore, we have some other technique to improve our scheme, which is bucketing idea. I'm not going to the much details about that, but just show some general ideas. So the bucketing idea is an idea to balance between the update time and the proof size, since ASVC has constant proof size and we want to make use of that. So the basic idea is to cut the vector into several buckets, and we attach a record list for each bucket, and we run the open all algorithm inside each bucket. And this method is not trivial, since we also want to ensure that the digest is still constant size, not the number of the buckets. So what we do here is to compute Lagrange interpolation over each bucket, and then another interpolation over the whole vector to get the whole polynomial. And our digest is the KZG commitment to that polynomial. Well, in this method, there's a problem that the public parameter to update is superlinear size. So we have a small improvement to make it linear, which is introduce 2 variables to indicate which bucket it is, and make sure that the update parameters is linear size. And in our final version, we use 2-layer bucketing, which introduce 3 variables. And finally, our protocol has n to the 1 over 4 log n update time and the square root of n proof size. So here is our performance and comparison. ASVC here is our input scheme. Basic compiler is our scheme without bucketing idea. And in our 2-layer bucketing, we pick the number of buckets so that our proof size is the same order as Hyperproofs. So you can see our proof size is 30 to 60 kilobytes or 50 to 100 kilobytes, which is almost the same order as Hyperproofs. And basically speaking, our scheme is a balance or trade-off between update time, proof size, and aggregation time. And you can see all of our parameters is of the practical sense. In summary, BalanceProofs is the first maintainable vector commitment with fast aggregation. And it has two parts. The first is a compiler, which balances the update time and the query time. And the second one is a bucketing idea to balance update time and proof size. And we have 3 types of bucketing techniques. That's all about our scheme. Thank you all.
Great.